Yo, Muso here. Let's talk about vectors a little bit more than what we already have. This is all about vectors, okay? And we're not even going to toss down too many other concepts other than straight up vectors, but of course with vectors there's going to be a lot of, well, you'll see. A vector, remember, anything has magnitude and direction, right? We often represent vectors vis-a-vis arrows. We've already talked about this, you've seen this a couple times. So that was 9 units long. I don't care what this is. Some vector, for the sake of simplicity, I'll label it right now, but it could be any vector. This could be velocity, displacement. It could be even forces, things that we haven't learned yet. I'm going to go ahead and say the velocity here, just to label it, is 9 units. So we'll say 9 meters per second. Straightforward. We've got that down, right? I can draw another vector that's only 3 units long. And you can tell vis-a-vis their proximity and size that indeed this is smaller, and we already measured it 3 units long. Easy stuff. This is straightforward basic vectors. What I need to talk about today is how to add vectors, how to put them together. When we're talking about one dimension, so if I were to draw my cardinal axes here, or maybe even we can consider this a coordinate system, x and y, I don't care. If we're dealing with just one dimension, vector addition and subtraction is very straightforward. It really is as simple as addition and subtraction. So it's good to define positive versus negative, and if you don't actually define it, then we're going to treat everything to the right as positive and everything to the left as negative. So I'm going to go ahead and do that. I'm going to say that this sucker is a positive 9 meters per second. If I were to then, let's say this is a car traveling, and then it experiences an additional, maybe a wind boosting it from behind of 3 meters per second. If I were to, I'll draw this off to the side first. If I were to go ahead and have that 3 meter per second velocity vector that I had there before, I want to ask you now, well, what is the final speed of the car? So I'm getting a little bit ahead of myself. First and foremost, this is the initial speed of the car. This is the speed that's being added to it. Since it's being added to it, since it's behind the car, it's going to boost it. So we could do this arithmetically. By just taking 9 plus 3, you know it's going to be 12 meters per second. Cool. We can also show this graphically by taking this vector and placing it on top of this vector in a method that we're going to call, that's called tail to tip. So let's talk about the vector itself. The base of the vector is the tail. The arrowhead, the end of that arrowhead, is the tip. An easy way to graphically show how we can add these two vectors together is to place the tail of one vector such that it ends at the tip of the other vector. So there's a few things you need to know about vectors. Vectors can slide or translate any way they want. Okay? I can take this guy and place it over here, place it over here. When you draw a vector, it doesn't show where the object was existing. It just shows the actual magnitude and direction of the vector itself. I cannot rotate the vector because that's changing the direction. That's bad. And I can't stretch it out or shrink it because that's changing the magnitude. That's bad. But I can slide it anywhere I want. So if I were to actually redraw this 3 meter per second vector such that its tail finishes at the tip of this one, let me do that real quick. Call it V2, and this will be V1 just so I don't confuse myself. Now that they're both on top of here, I can find what we're going to call the resulting vector or the resultant vector. What is the sum of these two vectors together? We already did it using our basic math. 9 plus 3 is 12. Let's do it using the graphing method. And all we got to do there is measure how long this vector itself is. And this vector is 12 units long. So I'm going to draw this again down here just so we can see them away from each other. But it's fine to draw it on top of it. That's not really a problem. But I'm going to draw the resulting vector. I'll do that in purple. By the way, you see I have new markers. I only have a few colors though. So to help represent, say, red, I'm going to use my old marker, which I don't really like, or some of my different hues of blue. I'm going to use my old markers, which I also don't really like. And my purple is pretty cool over there, but I've also got this lighter purple. So I'll use some of these markers, but they're starting to fade. I got to upgrade even more, really. I should just get like 1,000 different markers. That'll give me too many options. So anyhow, so I'm going to draw myself 12 unit long arrow. Bam, there it is. And because I measured it as 12, I know this is 12 meters per second. So my overall v, which sometimes we don't subscript at all. Sometimes we might put like a vt for total. I'm just going to leave v, is simply 12 meters per second. So that means this car that was going 9, that experienced a wind behind it of 3, will finish at 12. Easy stuff, right? And subtraction is pretty much the same way, but opposite, I guess. I don't know. It's where we take that vector. So let's say this wind was now whoosh, pushing against it. So I'm going to change my arrowhead. So it's still 3 meters per second, but now going the other way. Mathematically, I'm going to define this as positive and this is negative, so it'll be just 9 minus 3, or it'll have a final velocity of 6 meters per second acted against it, right? But we can also draw this, again, using the tail to tip method. I'm going to redraw that vector on top of the tip of my old vector. So the tail of my original vector will start here at the tip of the black vector, and it's going to finish right here, okay? So the black vector is my original 9. Minus that 3 velocity, I might as well label that up here. V2 is 3 meters per second. And since I have that arrow is drawn to the left, I don't need to write negative in here, but it wouldn't be a bad thing if you wrote the negative. So now I can measure my overall resulting velocity. Is once again, it's, look at that, 6 units long. So I can draw this. It's still to the right, that it'll still finish to the right. So I can draw this here, 6 units long. So my final velocity in this example is simply 6 meters per second. That's not too bad. That's pretty straightforward stuff. You're likely not going to graph one-dimensional vectors because it's just basic arithmetic. Really where the graphing method comes into play is when we have vectors in 2 dimensions. And that's going to be the bulk of this video, is 2-dimensional vectors. What happens when I have, and I'm going to teach projectile motion in a completely different lesson, but what happens if I take a ball and I project it, okay? If I throw it across. Okay, so one-dimensional motion, I roll it across the surface. Or I throw it straight up and it falls straight down. That wasn't straight, was it? Up and down. That's also one dimension. It's just in this dimension. So this dimension, this dimension. What happens when I give it 2 dimensions? What happens when I throw it as a projectile? Okay, perhaps you can see here that it's traveling in both the left-right dimension and the up-down dimension. It's hard to actually demonstrate this because of the top-down view of my camera. If I were to actually show what projectile motion looks like, it would be this parabolic path. All right, and now I could always turn the camera and throw it across the room, but I think you guys know what a ball traveling across the room looks like. So I'm going to draw that vector as a vector at some angle. I'm going to say that this vector, heck, I'll even give us I'll use a real protractor and everything. I'm going to say this vector is a 30 degrees above the x dimension. Okay, so I'm going to pull a plot there, a little plot there. That's 30 degrees. And I'm going to make it, I don't know, I'll make it 9 units long, just like the last one was. Why not? So I'm going to give this ball 9 meter per second velocity at some angle above the x, and I already measured that angle to be 30 degrees. Okay. This is a vector in 2 dimensions because part of it exists in the x dimension, or the horizontal dimension, and part of it exists in the y dimension. So a new thing that we've got to learn, well, first, before I even get into how to draw the vectors, a rule to learn, whether it's for velocity or forces or momentum, it doesn't matter. Any vector, the 2 dimensions are independent from each other. The x dimension does not affect the y dimension, and the y dimension does not affect the x dimension. They will come together to make my overall velocity vector or momentum vector or force vector, whatever it is. They will come together, but they are independent of each other. So we're trying to predict its motion, like where the ball will land. We have to consider only the x and only the y separate from each other, and you'll see when we get into actual projectile motion. For now, I just want to show you how to draw these vectors. So anytime you have a vector at an angle, you can always draw in what we call the component vectors. And the component vectors are the vectors that exist in solely the x dimension and solely the y dimension, or if it's like y and z, just solely those 2 dimensions, okay? So this is what we're going to label as v sub x, my x velocity of this 9 meter per second projectile. And this is v sub, ready for it? Yeah, v sub y. That's the y dimension. So my y component and my x component come together to make my overall velocity vector of 9. So how do I find out what these two vectors are? I mean, if I know the 9 meter per second horizontal, or not horizontal, hypotenuse, by the way, this is known as the, let me write these in. This guy, the one that's at the angle, this is known as the resulting vector, or the resultant. And it is the result of these two vectors. So these guys are known as our component vectors. We could call this the x component, and this is the y component. Any vector at an angle will always have always have two components that come together at a 90-degree angle to make it, to form it. So the x and y components will result in the 9 meter per second vector. So how do I calculate what these two vectors are? For that, we need to go back to our right triangle trig, our basic right triangle trig that we may have learned in math at some point in time. And if you haven't learned it yet, nice and straightforward, nice and simple. There's a little rule here. If you know two values of any of the 6 of a right triangle, you can find all the rest. So we have our hypotenuse and our 2 legs, and then we have our 90-degree angle and our 2 interior angles here. If we know 2 of any of these, we can find all the rest. So we do know 2. We know the hypotenuse and we know the angle. So there's this thing I'm going to write out here that a lot of teachers write out called SOHCAHTOA. Now I'm not going to teach trig right now because, well, this is a physics lesson. So if you need more help on this, I encourage you to check out some extra resources on that. YouTube is your friend. But for now, I'm just going to write out SOHCAHTOA, kind of write down what it all means, and then show you some math on how to find my x and my y components, right? So that stands for, if we were to say the sine of some angle, so the sine of my angle theta, S sine, equals my opposite leg of that angle divided by my hypotenuse. So sine equals O over H. And I'll translate this to my example in a minute. Cosine of some angle, the ca, is my adjacent leg divided by my hypotenuse. And then we've got the TOA, which I'll do in, I'm struggling, too many options, not enough options, oh my gosh. Okay, I'll do it in red. The TOA part says the tangent of some angle. See, I like the other ones better because they're finer tip, but I'll go shopping. The tangent of some angle theta is equal to my opposite leg over the adjacent leg. Cool. Remember this. This is true all the time. Anytime we have a right triangle, remember a triangle with a 90-degree angle in it, we can use our right triangle trig, or SOHCAHTOA. We get to use our fancy calculator to figure out some values. So I'm going to use this in the terms of this example here to find my components x and y. Yeah, protractor, get out of the way. So, I need a little bit more space, so I'm going to get rid of the component and resultant parts. This, but I'm going to leave that original triangle there. I'm going to get rid of this up here too, because I'm going to lose it. I want to find x and y. Before I do that, sure, I could also find my angle in here, right? Because they all need to add up to what value? 180 degrees. So 90 plus 30 plus x, it's going to be 60. Or these two always have to add to 90. So 30 plus what equals 90. So that's 60. But I'm not going to need it. I'm going to use this as my angle theta. Ready? Let's just do this. I'm going to say the sine of my angle theta, so the sine of 30, is equal to my opposite value over my hypotenuse. So it's going to be equal to my opposite value. That's an unknown there. V sub y. I could put x if I wanted to, or O. I prefer to put the physics variable there so I don't forget what I'm doing. Over my hypotenuse. And I'm going to leave it in the variable format first. So it would be sine of theta equals Vy over V. And I guess if I really wanted to be particular, leaving it in my variable form first, I'll just do this. So sine of theta equals Vy over V. And maybe I'd call that theta 1. Because this would be probably theta 2, right? Now, I know theta 1, that's 30, and I know V, that's 9. I could write that in. Theta 1 is 30 degrees, and V is 9 meters per second. So I want to isolate Vy. So I'm going to multiply, I'm going to carry that V over to get Vy by itself. Vy will be V times the sine of my angle theta. This is a pretty typical setup. We typically once we get used to our trig, jump right to this line. We don't start here. I'm just doing this so you can see where it comes from, but often we'll say the y component is equal to v times some trig value, and the x component is equal to v times some trig value. So in this example, it's going to be v9 times the sine of 30. Now I understand, I know what sine of 30 is pretty quick in my head, but I'm going to go ahead and use the calculator just so we can show you how to do that. I like these graphing calculators. If you use a scientific, you might need to go backwards. You might need to do your trig first and then multiply by the 9. I'm just going to do 9 times, ready? Magical, right? 9 sine 30. And you don't even have to close that parentheses. It's just habit. I choose to do it. And, oh, wow, that's way wrong, right? That's negative. That's crazy. How come that's like that? Don't write down some absurd value. You know it's not negative 8.89. Is it pointed that way? Or, I'm sorry, this is the y, right? Is it pointed down? Negative is down. No, something's wrong. Let's go to my mode. Oh, that's what it is. I'm in radian mode. You go over to degree. Always make sure your calculator's in degrees when you're doing trig. I'm sure your math teachers have hammered that in over the years, right? 4.5. That is so much more logical. So 4.5 meters per second. Also, it's helpful to know that sine 30 is 1/2. Cool. Now we know Vy is 4.5 meters per second. Now I could then go ahead and do Pythagorean theorem to find Vx, as I know a squared plus b squared equals c squared. If I know c and b, I can find a. I'm not going to do that. I want to do some trig just to show you how to do it. So I'm going to go ahead and say Vx, or no, actually, let's go. I'm looking for Vx. What leg is this? This is my adjacent leg, because remember, although there are two legs adjacent to this angle, adjacent means next to it. This guy is my hypotenuse. The hypotenuse is always the longest one, the one opposite of my 90. So the other leg is my adjacent leg. This is A. So I have A, or I'm looking for A. I have H, my hypotenuse. I'm going to use cosine. We're most often using sine and cosine. You rarely will use tangent. That's a little heads up. So the cosine of my angle theta is equal to my adjacent value, Vx, divided by my hypotenuse, V. And the knowns are still true. I'm going to get Vx by itself. Vx is equal to, I'm going to multiply that V over, V cos theta. And again, this is typically the way we start these problems off. We don't start here, we start right here because we know this is true. So V is going to be 9 times the cosine of 30. Now cosine of 30 is not 1/2. There is a cos function that you can remember. I'm going to just go ahead and type it in anyhow. 9 cos 30. 7.79 meters per second. I'm going to round that up to 8. Rock on. And it's positive, so it's to the right. Good. Those are my x and y components. Easy stuff, right? Might forget some of this easy stuff, so I encourage you to practice this so you don't forget it. But that's all you got to do for right triangle trig with vectors. Now, there are, of course, there's more to this, and I'm going to do another example on vectors in the next video. All right, there you have it. Cool. I'm going to end this video, and we're going to just do more vectors in the next video. Thank you.